It's like a super smart toy. Have you ever played with building blocks? You can stack them up high to make a tower, or line them up to build a long wall. A computer is a little bit like a giant box of super smart building blocks. But instead of building towers, it builds answers to questions. Imagine you ask your computer, what is 2 plus 2? It doesn't just guess. It uses its special blocks to figure out the answer is 4 every single time. It's a fantastic helper that can play games, show you cartoons, and help you learn about dinosaurs and distant stars. Think about a recipe for making cookies. First, you mix the flour and sugar, then you add the eggs, and so on. A computer is amazing at following recipes, which we call programs or code. These recipes tell the computer exactly what to do to solve a problem. Whether it's finding the fastest way to get to grandma's house or helping scientists discover new medicines, the computer follows its instructions perfectly. It's like having a super fast, super obedient robot helper that lives inside a little box, ready to tackle any puzzle you give it. Now, what if you had a toy that could follow millions of instructions in the blink of an eye? That's what makes our computers today so incredible. They are experts at doing simple things very fast. They can check things off a list, add numbers, and compare things. This speed is what lets you watch a movie without it stopping, or play a video game where everything moves smoothly. The computer is doing millions of tiny jobs every second just to make that happen. It's a powerful tool that has completely changed our world. But all these computers work in a very specific way. They use a simple secret language to do all their incredible work. A language of only 2 words. Understanding this simple language is the first step to understanding an entirely new kind of computer, one that works in a way that feels like pure magic. So, are you ready to learn the secret code that powers our digital world? Let's dive in and explore the tiny building blocks of information. Imagine your bedroom has a light switch. It can only be on or off. There's no in between. A regular computer thinks the same way, but with billions of microscopic switches called bits. A bit is the smallest piece of information, either 1 for on or 0 for off. This simple language of zeros and ones is called binary code, and it writes everything. Your name, your favorite song, a cat photo, a whole movie. For example, the letter A might be 010000001. String together billions of bits, and computers can represent complex information and process it. One switch could answer yes, no. To represent numbers like 5, you use patterns across multiple switches. Pictures can need millions of bits. Games, billions, or even trillions, all flipping fast. That's classical computing. Reliable, predictable, and incredibly powerful when you use enough bits. A bit is either 0 or 1 like a light switch. But what if a switch could be both on and off at the same time? Welcome to the weird and wonderful world of quantum physics. Picture a spinning coin. While it twirls, is it heads or tails? It's neither, or in a way, both at the same time. You only know when it lands. That spinning coin is a great way to think about a quantum bit. A qubit. A qubit is the building block of a quantum computer, just like a bit is for a regular one. But unlike a bit, a qubit can be 0, 1, or both at the same time. This is called superposition. It's not a trick. It's a real property of tiny particles like electrons and photons. Scientists build qubits to harness this natural quantum behavior. 3 classical bits store one combination at a time, like 101. 3 qubits can hold all 8 combinations at once. It's like exploring every path in a maze simultaneously. A regular computer checks possibilities one by one. A quantum computer tries many at once thanks to superposition. It isn't just faster, it's a completely different way of solving problems, one that opens up possibilities once thought impossible. Gently. Let's explore this idea of superposition, the secret sauce of quantum computing. Imagine a giant library with millions of books. A classical computer is like a very fast librarian who checks each aisle, each book, and each page one by one. It works, but big libraries can take days, years, centuries. Now a quantum librarian can make copies of themselves, go down every aisle, check every book and every page, all at the same time. That's superposition, not just a 0 or a 1, but a blend of both. It lets quantum computers process lots of information in parallel, making them incredibly efficient for certain problems. When we're not looking, a qubit is in a cloudy state of possibilities. The moment we measure, are you 0 or 1? The spinning coin lands. The superposition collapses and the qubit becomes a definite 0 or a definite 1. The trick is to design quantum recipes, algorithms, so that when qubits collapse, they give the correct answer to the problem. This makes quantum computers fundamentally different. For big variable problems, designing new molecules or breaking complex codes, classical machines get bogged down. Quantum systems can sift through massive possibility spaces in a fraction of the time. Okay, as if being in two states at once wasn't strange enough, qubits have another superpower: entanglement. Einstein called it spooky action at a distance. Imagine two spinning coins magically linked. You keep one, your friend flies to Australia. When you look and see heads, you instantly know theirs is tails, no matter the distance. It seems faster than light, but it's not sending messages. It's like they're parts of one unified system. Measure one qubit and you immediately know the state of its partner. Entangled qubits work together, creating complex multi-qubit states that hold and process exponentially more information. Combine superposition and entanglement, and you get calculations beyond classical supercomputers. Classical bits act independently, entangled qubits act as a team. The whole is more than the sum of its parts. This teamwork enables complex quantum algorithms that could change our world. So, let's put it all together. What's the difference between your desktop and a quantum machine in a high-tech lab? A classical computer is like a super-fast, organized librarian, amazing for most tasks. Searching, sorting, calculating step-by-step, browsing, writing essays, and playing most games. For 99% of what we do, classical computers are perfect. A quantum computer is like a library of magic books, about every topic at once, with a librarian who reads them simultaneously. Not helpful if you want a specific known book, a classical librarian would be faster. But if you're finding a single unique idea hidden anywhere in the library, the quantum librarian shines, looking everywhere at once to find that hidden idea. Quantum computers won't replace your laptop for email or videos. They're special purpose machines for problems classical computers can't handle. Problems with huge combinations, scientific research, complex optimization, discovering new materials and medicines, simulating how molecules behave. Molecules are quantum systems. Quantum computers simulate them well. Classical machines often approximate. The future is a hybrid, classical and quantum together. Classical handles the interface, stores data, sends instructions. When a quantum-sized problem appears, it dispatches that part to a quantum processor. Quantum uses superposition and entanglement to explore vast problem spaces, finds the solution, then sends the answer back. The right tool for the right job. If they're so powerful, why don't we all have one yet? Building and controlling quantum computers is one of the biggest scientific and engineering challenges of our time. Remember our spinning coin, the qubit? Its superposition is incredibly delicate. Tiny temperature changes, stray vibrations, or electromagnetic noise can make the coin fall over. This is called decoherence. When decoherence happens, the qubit loses its quantum magic, collapses to 0 or 1, and the special calculation is ruined. To prevent this, scientists go to extraordinary lengths. Quantum computers often live inside massive, chandelier-like dilution refrigerators. They cool chips to a fraction of a degree above absolute zero, keeping particles still so they don't bump qubits. Systems are shielded from interference, vibration-proof labs, magnetic shielding, all to protect fragile states. Getting information in and out without disturbing qubits is monumental. Scientists use precisely controlled microwave pulses and targeted beams to nudge qubits into superposition, entangle them, and guide calculations. It's like microscopic surgery on invisible, hyperactive particles. The level of precision required is astounding. We have dozens or hundreds of qubits today. Useful algorithms will need thousands, even millions, of stable, interconnected qubits. As you add qubits, errors and decoherence grow. Research focuses on quantum error correction, using extra qubits to detect and fix errors without destroying the quantum state. It's an immensely complex puzzle tackled by brilliant teams worldwide. If you want to go deeper than analogies, let's peek under the hood and see how quantum computing really works. At its heart, a qubit state is a vector in a complex two-dimensional Hilbert space. The basis states, ket 0 and ket 1, correspond to classical 0 and 1. In superposition, a qubit is a linear combination, alpha ket 0 plus beta ket 1. Alpha and beta are complex probability amplitudes. Quantum gates are unitary operators rotating state vectors. The Hadamard gate turns ket 0 into an equal superposition, ket 0 plus ket 1, a 2. Gates like C and naught create entanglement. A quantum algorithm is a carefully choreographed dance of such operations. And classical bits represent one of two circumflex n states at a time. And qubits are described by two circumflex n complex amplitudes. 3 qubits need 8 amplitudes. 10 need 1024, around 300 would exceed atoms in the known universe. Wild, right? Quantum computers manipulate all amplitudes at once, quantum parallelism. In the end, measurement collapses to one basis state, with probabilities set by the amplitudes. Algorithms like Shor's and Grover's use interference. Wrong answers cancel, right ones amplify, boosting the chance you measure the correct result. The promise of quantum computing isn't faster video games, it's solving humanity's biggest, most complex challenges. Designing new drugs and materials requires quantum-accurate molecular modeling. Classical machines struggle, quantum could model interactions accurately and speed discovery. Optimization in logistics, finance, and engineering can overwhelm supercomputers. Quantum algorithms like QAOA aim to tackle these, saving fuel, improving models, and smoothing complex systems. Powerful quantum machines could break today's encryption with Shor's algorithm. That sparked a global race for quantum-resistant cryptography. Quantum machine learning may reveal patterns invisible to classical methods, enabling more intelligent AI, more accurate medical diagnoses, and stronger climate models. It could push the boundaries of what is knowable. We've used words like magic and spooky. But the most incredible thing is, it's not magic. It's real science. We're still in the early days, like the 1950s of classical computing. It's a marathon requiring physicists, engineers, and computer scientists. Every qubit added and error reduced brings us closer.